Today we are diving deep into one of the most demanding and critical aspects of iron making, optimizing blast furnace performance with a specific focus on managing raw material quality and fines for stable operation. This topic is crucial for ensuring the efficiency and longevity of our blast furnace operation. So let's get started. The blast furnace is a complex system, as we all know. To set the stage for a complex furnace, let's briefly revisit what a blast furnace is. It's tall vertical shaft furnace whose primary purpose is to produce molten iron from iron ore for the subsequent liquid iron production. This is not just any piece of equipment, it is a complex and massive production system with many interconnected facilities. Our blast furnaces operate continuously, achieving very high availability, often over 95% of the time. The sheer scale of production is impressive, with typical daily output ranging between 4,000 to 12,000 ton of molten iron per furnace. The daily operation conducted by our foremen, ship managers are absolutely crucial for maintaining a stable performance. A key tool for effective management is understanding the smelting process curve, also known as operation curve. This dynamic display shows real-time changes in main parameter like blast volume, pressure, top gas pressure, stock line. It's considered the magnifier and the microscope of the blast furnace smelting process, providing vital reference for daily operation. At its core, the ultimate objective for operating a blast furnace are clear and can be summarized by 5-point policy. First is to produce the largest quantity of qualified pig iron. This speaks to productivity and meeting demand. Number two is achieve the lowest unit consumption of raw material. This focuses on efficiency and cost reduction. Point number three is ensure the longest service life for the blast furnace and their accessories. Uh, um, and the fourth is guarantee the safety of blast furnace workers. Safety is of course paramount in any industrial setting. And the fifth point is finally achieve low consumption and longevity in combination with safety. This policy is often encapsulated as high yield, high quality, low consumption, longevity, safety. So every decision, every adjustment should align with these over these goals. Now coming to the our next slide, which is on the critical role of raw material. Now let's talk about the fuel that drives this giant, the raw material or the burden. The ferrous burden primarily consists of lumpur, sinter and pellet. In addition, coke typically containing around 85 to 87% carbon along with the fluxes are charged from the top of the furnace. Optimizing burden use is a vital topic in blast furnace operation. It requires establishing a proper standard for blending and proportionating this material. The quality demand for the blast furnace burden are absolutely crucial for proper performance. The nature of this ferrous burden directly impacts key operating parameters, most notably productivity and the slag rate. For example, pellet are becoming increasingly important for pig iron production, especially in regions that rely heavily on imported ores like Japan or Western Europe. Their use is also growing in Europe as a means to reduce cinder production due to environmental concern. Now coming to our next slides about challenge 1, which shows the low temperature disintegration and swelling as a one of the big cause. One of the primary challenge with raw material quality is related to their behavior during reduction, that is known to all of us. The first low temperature degradation, LTD, this occurs when hematite is reduced to magnetite, generating energy and creating internal tension in the crystal structure. This tension can cause the burden material to break down into smaller pieces or particles. Various tests are available to quantify this. Closely related is pallet swelling, which also occurs during the reduction, while a volume increase of up to 20% is generally acceptable and doesn't significantly harm the furnace operation. A greater increase is considered abnormal or even catastrophic and must be avoided. The significant impact of both LTD and excessive swelling is on the smooth and regular descent of the burden within the furnace. They can lead to issue like burden hanging and slipping, which directly interfere with the efficient reduction and melting of the ferrous raw material. Coming to the challenges too, where we can say that it is all about these challenges that significantly impact blast furnace operation is the presence of fines. The impact of fines, of course, we can say that in challenges number two, the impact of fines we are going to analyze. Another critical challenges that significantly impact is the presence of fines and the causes of fines. These small particle can originate from various sources. For example, pulverized coal injection, especially at high injection rate, can lead to a significant increase in fines generation. Additionally, coke degradation within the furnace also contribute to a amount of fines. The detrimental effect of fines on the furnace operation are manifold. They can severely impede the gas flow and the permeability of the coke column. A major problem arises from the accumulation of fines in the deadman, which is the central, relatively inactive coke zone in the hearth. This accumulation drastically reduces the permeability of both gas and liquid flow, leading to poor tapping ability of the pig iron and slag. The furnace's inherent capacity to consume these fines through the solution loss reaction is limited, which puts a ceiling on how much coal can be injected. Now, beyond physical properties, chemical impurities pose a significant challenge. The presence of alkali metal, particularly sodium and potassium, in blast furnace material can lead to a subsequent operational problem. At the highest temperature found within the furnace, this alkali metal can cause excessive swelling of the ferrous burden. This makes the material porous but also compact and difficult to move, thereby severely impairing gas flow. Furthermore, alkalis are known to contribute to the formation of a scaffold and scaps on the furnace wall. This buildup causes irregularities in the furnace behavior, leading to a undersizable event such as hanging and slipping of the burden. It's important to monitor the concentration of sodium potassium in the burden, as normal input amount can range from negligible to approximately 10 kg per ton hot metal. Now coming to our next slide, which speak about that how do we mitigate these challenges and ensure a stable furnace operation. So first, burden optimization. It's crucial to establish a proper standard of blending and proportionating the burden material. This is a fundamental for optimal burden utilization and for controlling the composition of the slag, which is the way which is the very foundation of blast furnace process. Next, coke quality. Maintaining good strength and larger size of coke is absolutely essential, and this ensures the permeability of the stock column and keeps hearth alive and active during the blast furnace blowing. Slag composition control is also one of the most vital activity. The slag analysis critically influences the hot metal quality. As the saying goes, the better the slag, the better the hot metal. Slag composition can be adjusted by adding fluxes like silica, CaO, MgO to achieve the desired properties. Silicon content in hot metal is also one of the important activity, and keeping the hot metal silicon at a proper level typically around point 0.6, point 0.7, silicon is vital. If silicon is too high, the hot metal can become excessively viscous, and if it is too low, manganese recovery might decrease significantly, and there is a risk of hearth agglomerating, potentially damaging the tuer. Also, finally, while titanium bearing material can be used for furnace fettling or lining protection, excessive amount must be avoided, as this can lead to accumulation in the hearth and operational damage. In modern blast furnaces operation, advanced control and monitoring system plays a pivotal role, and process curves analysis, as mentioned earlier, the smelting process curves is a dynamic visual representation of key operational parameters. It provides shift executive with a crucial real-time information to guide their operations and is indispensable for blast furnace chief and smelting engineers to deeply understand and master the blast furnace smelting process. Expert system and automation is also one of the new time development of blast furnace mathematical models and control. These data uh, also going to be a very helpful. Building on this expert system for furnace temperature adjusting have been developed to aid in automation and improve decision making. Such system continuously monitor relevant parameters, standardize operation, and can even trigger alarms or action when parameters deviate from target ranges. Hearth monitoring temperature detection is the primary method to monitor hearth bottom. Changes in the cooling water temperature, difference of step coolers provide timely indication of corrosion or health actively. Thermocouples and galvanic couples are also employed to calculate corrosion depth. Furthermore, similar to coal-fired power plant, advanced sensors and smart controls are continuously being developed and refined to enhance monitoring and operational precision. Now, coming to the iron making industry is constantly evolving, driven by the demands for increased efficiency and critically decarbonization. Increased campaign life, blast furnace designers are actively working on understanding hearth wear and developing technologies to achieve an impressive 20-year campaign life at high productivity rates. As far process optimization is concerned, the inherent complexity of the blast furnace makes it a non-linear system. Therefore, non-linear optimization methods such as the generalized reduced gradient in Excel solvers are employed to determine the best operating condition for specific goals like achieving the lowest production cost or minimum coke consumption. Decarbonization effort, this is a major area of focus. One promising avenue is the use of hydrogen as a reducing agent. Replacing coking coal with a hydrogen can almost entirely eliminate CO2 emission from the blast furnace, producing water instead of CO2, especially if hydrogen is produced using renewable energy. This is a significant step towards green steel. Carbon capture, utilization, storage is considered to be one of the most effective method for deep emission cuts. The technology is mature and can retrofitted onto existing asset, allowing a steelmaker to maintain their current production infrastructure. So, in the key takeaways to summarize our discussion today, let's look at a key takeaways. Stable blast furnace operation is a paramount for achieving high yield, maintaining product quality, and ensuring the longevity of our assets. The quality of raw materials directly impart furnace performance, emphasizing the need for meticulous preparation and blending of the burden. Successfully managing fines and preventing excessive swelling are critical challenges as they directly influences gas flow and health permeability. Alkali metals are persistent impurities that require intelligent control to avoid significant operational issues and furnace instability. Continuous monitoring using dynamic process curves and advanced sensors is essential for making proactive and informed operational adjustment. Finally, the iron making industry is inactively pursuing innovative technologies for both efficiency improvements and decarbonization, including hydrogen injection and carbon capture solution. Your team's understanding and skillful application of these operational principles are absolutely vital to the continuous success and evolution of our blast furnace operations.